In this session, we will discuss about tree representation. A tree is a non-linear data structure. To make the uh, data representation of some complex element, it will be possible using this kind of non-linear data structure, trees. So it is a hierarchical data structure. Okay. Next, a binary tree is made with the number of otherwise collection of nodes. Each node contains one data element, one left pointer and right pointer. Okay, this is the basic representation. And how can we represent a binary tree? We can represent a binary tree by using either arrays or linked list. Okay, how can we represent in the arrays fashion? So you know that an array is a collection of similar items. All the elements will be stored in a continuous memory location. Here the data will be stored using arrays is level by level. Okay, level by level, nothing but, so level 0, nothing but from root element, then first level, second level, up to last, up to the siblings and so on. Okay, just from the level 0 to the last siblings to the data will be represented level by level. Okay, next, these kind of nodes will be represented in arrays is one dimensional array. It's a representation using the one dimensional array. Next, the node can be stored in the first memory location as the first element in the array. Okay, so we have to follow the some of the rules. How can we represent a tree using arrays? We have to follow some of the rules. What are these rules? For the parent, suppose we have the tree and each tree having left node and right node. Again, a left node may contain one more subtree. Okay, right node also contain that much subtree. Okay, just like that, how can we represent these kind of subtrees and collection of trees? So these will be represented some parent. Again, parent have the child, and child will be one of the parent. Again, child is the, it might be the parent. Just like how can we represent an array representation using this kind of structures. So here parent nothing but we have to calculate this parent is some I. Suppose some level from 0 to the up to, suppose I have stored these elements from 0 to the 8, 0 to 8 mathematics 9 elements. So for parent I is equal to n minus 1 by 2. For left cell representation 2 into I plus 1. For the right cell representation 2i plus 2. So you have to calculate the below diagram and we can check that. Suppose from the level 0, 0 nothing but we know that array representation is by the level by level. Okay, next, suppose A having the two childs, one is B left and E is a right child. So for 1, how can we represent left child? Nothing but 2 into I plus 1. 2 into I nothing but 0 plus 1. 2 into 0, 0 plus 1, 1. So B is the first child, 1. Next, how can we represent the right child? Right child 2 into I plus 2. 2 into I nothing but 0. 2 into 0, 0 plus 2. So 2. So right representation E is the 2. So just like that we can create otherwise we can represent a tree using arrays, just like this simple rules. Okay, so the data will be stored in the level by level fashion, and by using this kind of parent representation, child representation, 2 into I plus 1, 2i plus 2. So we have to represent like this tree and subtree fashion of the binary tree. Okay, so this is the basic representation of array representation of the tree. Suppose if you want to create a binary tree, otherwise making a binary tree using the linked list, how can we create that? You know that tree representation will be done by using the some hierarchical fashion, otherwise it will make the some complex relation. Just like, look at this here. Suppose for the first one is the left child, next data element right child. Okay, so you already see the basic first representation here, this like this. So what is that? First, the first element parent, next child, and left child and right child. For every node has the data element, left pointer and right pointer. Likewise, we can see that a simple diagram, parent oval shape I have shown here, parent root and child, left child and right child. Suppose a simple example I have given here. Is it visible or not? You can understand this. Look at this picture. So the basically what is the diagram here? Some parent A. Next, Okay, parent A, child B. B has the one subtree. B childs are D, E, and C childs are F and G. G again one more subtree. G has the H and I children's. So these all D, E, F, H, I, all the leaf nodes, all the leaf nodes. So how will be represented in the memory? So this is the memory location. Look at this memory location here. Left child, data, and right child. Left child, right child. So suppose D element have the address some 500. B has the address some 750. So we have to link up all this left pointer and right pointer. So basically root is the A. Next left pointer is B. Pointer linking up. And next C is the right pointer. C has the right child, so right pointer has to link up to the A node. Okay, so basically first we have to see this here, the linked list representation here. So first is A, we have the pointer 750. What is 750 address? B address is the 750. So 750 will be stored in the A's left address, and 460 is the address of C. 460 is the address of C. So that is stored in the right pointer of the root element A. Okay, again B is the node. B has the one more subtree. B's two childs are 500 and what is that address? 400. So 500 left pointer and next one is the 400 is the right pointer. Likewise, and C has the one more left child is F and right is G. Okay, like that we can see that how the data will be represented in the memory location will be addressing just like in the table format. So 500, what is that? D. 750 B. So by the address we can link up all the elements. So pointer is helping to the pointing the data elements. So left pointer, right pointer representation will be done in the double linked list. So like this we can represent the data. So before that in the arrays we are representing in the level by level. Here we are representing the some left pointer pointing and right pointing. So like this we can represent the day some complex elements, some complex data making the relation. So here relation nothing but B has the two childs and B is the child of A. And see the diagram here. What is the diagram here? So B is the child of A and D are B. D are the childs of B. Just like the relation of B is the relation making with the D and E childrens. A is the making the relation with the B and C. Just like that we can make some complex relations, some networking relations. Okay. Next. We can understand all this even though we have some drawbacks. We have some drawbacks. What are the drawbacks? So the drawbacks are sequential representatives are overcomes it. Even though array representation is a representation having some drawbacks, these are overcome by using this representation, linked list representation. But we may or may not know the depth in advance. So we cannot find the depth in advance. And in addition, for unbalanced trees, the memory is not wasted. So we have to know one that we should not waste the memory. We should not waste the memory. So in the sequential memory, nothing but by using the arrays, it is helpful. Even though, so it these what is that? Drawbacks are overcome by the linked list representation. Okay. So we should not waste the memory. Insertion and deletion operators are more efficient in this representation. Okay. So the basic representation of the linked list, we should not waste the memory. We already know that dynamic memory allocation nothing but we should not waste what how much memory we need, that much we are using. If you want addition, we can additionally we can insert the memory. So by using the array static representation of arrays, it is a fixed. It might be used the suppose I have used some 20 size of array, we might be used 20 or not. If we need the more than the 20, we cannot. So insertion deletions are not possible by using the static memory. By the dynamic, we can insert the new data and delete the wastage of data. Nothing but by the linked list, nothing but by using the pointer, we can efficiently use the memory. So we should not waste the memory. And easy representation of insertion. Suppose I want to insert a child to the particular leaf node. we can insert. If you want to delete some data, so these kind of insertion and deletion operations are more efficient in this kind of representation, linked list representation. So, and it is useful for the dynamic data. You already know what is dynamic. Dynamic nothing but additionally we can add the data in any point of time. We can remove the wastage of data, unnecessary elements also we can remove at any point of time. Okay, these are the basic advantages of the, so not the drawbacks, advantage of the linked list. Okay, next, how to implement. So just we already we have discussed only what is a tree, what is a representation, what is a binary tree. So we didn't come to the implementation, programmatical representation. How can we represent? So we can represent by using arrays and linked list. We can implement either implement using linked list. So if you want to make the using the linked list is more convenient because already just 1 minute back I have discussed that is a very best for the insertion and deletion using the linked list. So what is that? Here the linked list representation is more convenient. What is a traversal? Traversal already discussed in the stack representation. Traversal nothing but it's a process to visit all the nodes. If you want to display all the elements, if you want to see what are the elements in your data structure, the process we have to call is a traversal. Just like display function we are using, so like that we are traversing the all the node data. Okay, all the nodes existed in your non-linear data structure and linear data structure. So here one thing we have to know. So what is that? So every node is connected with the edges nothing but links. Every node is represented in the using the edges. What are the edges here? Links. So we have to call that as links. Here see the edges, and we always start from the root node. We have to start from the root node. So if you want to create a tree, we have to start from the root. If you want to traversal a tree, we have to start from the root. So all these nodes will be connected with the edges, nothing but links. So what is the traversing? We already know what is the traversing, nothing but visiting all the nodes existed in a particular tree, particular data structure. Suppose here we have the two best traversing techniques. So these are very important traversing techniques and very helpful in practical also. What is the traversing techniques? Are two traversing techniques, breadth first search and depth first search. Okay, so what is breadth first search? Breadth first search is nothing but it's a traversal where the node is visited before its children. Nothing but first the root node is visiting nothing but going to look at that node, root node, and next the children. So that is the breadth first search. So what is the depth first search? Where the children are visited prior to the parent. Nothing but first the children are visited, next parent is visited. What is that? We can understand the later. So in this session I want to discuss only breadth first search. Okay, next session we will discuss the remaining searchings. So traversing. So here what is that here? So first we have to know that a traversal where the node is visited before its children. So breadth first search is nothing but a traversal where the node is first visited, nothing but root is visited first before its children. Next, these are the, in this breadth first search we have the three ways of traversing. In this search we have the three ways. So what are those? Pre-order traversal, in-order traversal, post-order traversal. What is that? Pre-order, in-order, post-order. So basically these three. Pre-order nothing but, look at this, what is a pre-order? Pre-order nothing but in this traversal the root is visited first, then the left subtree is pre-ordered, and finally the right subtree is pre-ordered. Suppose I have a tree here, look at the example. With the example we can understand easily. After that example I will explain the algorithm. You can say what is the algorithm for the particular order. So here what is the root here? Root is A. Root is A, and B is the child and C is the child. B is again one more subchild. C is one more subtree. B is a subtree and C is one have the some subtree, sub-left tree and sub-right tree. So in that what is the pre-order? Pre-order nothing but you have the tree travels pre-order, in order, post order. So pre-order nothing but we have to visit the first node, root node we have to visit the first. What is the root here? A, first root we have to check, and we have to move to the left child, again left is a one more subtree. So subtree nothing but in that B is a root, so we have to visit the first B, next we have to visit the D and E. Okay, so first we have to traversing nothing but first root element A, again B, next D and E. So if we have D has one more subtree, then we have to go to the D and D's children's. If I have the D subtree, so we have to go to the E's subchild subchildren's. Okay, like that. So in the pre-order we have to visit the first root node and next to the subchild pre-order traversing and right child pre-order traversing. So every subtree we have to follow the same pre-order, every right child we have to follow the same pre-order nothing but visiting the first node and next left subtree pre-order traversing and right subtree traversing. So in this output we can check that first A visiting the root, next B visiting, and next B has the subtree, next D and E, and next so left child hierarchy is over and move to the right child, right subtree. So E has the one more subtree, so C has a subtree, and these children are F and G. So this is the pre-order. So this is a simple example. Suppose if D, E, F, G, these are the siblings, these also some of the subtrees also we can go follow the same rule, the pre-order of the particular binary tree. So pre-order to the particular siblings, subtrees. Okay, so this is a very simple example. So what is the algorithm we can write? So first step we have to visit the root node, next traverse nothing but visiting the left subtree. Suppose if the left child is a one more subtree, we have to follow the same pre-order for the subtree. Suppose subtrees children are having some more subtrees, we have to follow the same pre-order. Just like that we have to visit the left subtree traversing. Next third step we have to traverse the right subtree of the particular tree, binary tree. So this is the basic example, basic order for the pre-order. So in this we have I have given the how to write a simple program, simple implementation of a tree, and how to do with the pre-order traversal in the birth first search. Okay, so the program is not difficult, very easy to understand. So what we need here? We need a tree. So here what we have to know, so we are representing using the linked list, and every node having the three things. One is the left pointer, right pointer, and data element. Okay, so every data will be nothing but node will be connected to the children's, nothing but with the edges linkings. So by using the pointer, nothing but by using the dynamic memory allocation, we can create every time insert the new node, delete the particular node. So how to create? Here I have used the just a simple pre-order function I have given. Suppose I want to create a particular suppose pre-order traversal. So if root has no subchilds, we have to check that. By using that root is a null, we cannot see, so tree is a empty. If it is not, nothing but pointer is not null, so we have to traverse all the elements. Left element first is a root node, root nothing but first is the data element, and left child and right child. Just I have given only simple function for the particular pre-order. Basically this is the particular perfect program for the pre-order traversing. So go to the program, it is easy to understand. So pre-order, so from this we can carefully observe that we have imported java.utility and scanner. So we have to read the data, CNN here scanner, and I have used the binary search tree nodes. I have used the binary search tree node class name. So in that I have created left and right nodes. So what that binary search tree nodes is a class name, left pointer and right pointer. I have created the two nodes, and we need the data element. So every node having the two pointers, left and right, and data element. Data element is it might be integer, float, whatever the data. I have used the integer kind of data. So I have created one constructor, down public binary search tree nodes are left is null, right is null, and data is 0. So and again I have created one more constructor with the data D, argument constructor. Argument constructor created left null, right null, and data element particular D. So D is an argument from the memory creation execution time. So what we have to do next? So every node has to link to the left and either right child. So we have to set the left. Here how to set the left? So public void set function set left binary search tree nodes. So I have to use the n variable. So next nothing but some node we are setting the left. So for the left is a pointer because left is a binary search tree object. Left is a binary search tree object. So left is n nothing but it will become from the execution time. So what how to set right? Set right nothing but is also one of the argument setting from binary search tree nodes some n. So we are linking the right to the n. Again get left nothing but getting the data of the particular left element, left node, right node, like that. So how to get that here? Get left, get right is the so everything here if you are using integer kind data we are using the integer value, float value. Just like here we are using the binary search tree node, that is a class name, class type of object, class type of data we are using. Like that we are creating the element. So just that we are using public get left function is the public binary search tree nodes get left, getting the left node. So returning the left, return nothing but we are returning the binary search tree type of left node, binary search tree nodes of the kind of left node, just like the right get also. Okay, so we are just only pointing solely we are setting and getting the left and right. Suppose I want to set the data. Okay, we have to set the data, nothing but every node have the some particular data. So the data is a integer type. We already created data variable initially in the class declaration. So data getting from the integer data. So d will be initialized to the data. Get data in it, but what is the data inside the particular node? By using the get data function we are using returning data is a integer type, so we have to use the integer type of or return type. Again, so up to that a simple node is created, nothing but getting set the data. These are the basic functions of a binary search tree nodes. Again we have to create one more class, that is a binary search tree. In that we have to create the linking these nodes. So in that in that binary search tree nodes of node. So what is the root here? Root is what kind of data, what kind of node? Binary search tree tree nodes of data. So root is a node. What kind of that? It's a binary search tree nodes type. Okay, in that we have created a constructor with the class name binary search tree is a class name. Binary search tree is a class name. With that we have used the constructor. So here our class is the binary search tree and our constructor is the binary search tree. The first line here, private binary search tree nodes, nothing but root is a type of binary search tree type of nodes. So we have used the private nothing but in this particular class only it will be accessible. Okay, for the constructor of binary search tree is the root is null. So nothing is linking to the particular data, nothing but no node is created. Suppose public boolean empty. Suppose to see the empty condition, empty nothing but returning root is null. Empty condition nothing but the root is null. Next, avoid if you want to insert a node, nothing but insertion and deletion are very possible. Whenever we need we can insert. Without dynamic we cannot dynamically insert the data. For the arrays it's a fixed size, but here we can create any time, insert the new data, delete the particular unnecessary node. Okay, here I'm inserting the node. How can we insert here? Suppose by using insert function we are inserting. So root here I'm inserting with the initially we don't have any tree, no node here. So root is a node. Root is inserting to the root and data element. Next, what is that insert function? How to write the insert function down? So what is that? Private binary search tree nodes of what is this function name? insert function of the particular what class? Binary search tree nodes of. So first class we have created, that kind of node we are using, and that kind of data will be created. So inserting, what kind of inserting? We are inserting a node with the data. So here the function is used starting here, the root insert root data. That insert is actual definition, function definition is returned here. So insert function, binary search tree nodes and insert data. Next, if node is null, so if don't have any tree, so if null, nothing but the node, we are creating the node is equal to new dynamic memory creation, binary search tree nodes data. So if it is not null, then we have to go to the null. So what is right and left? So if the data is less than or equal to the get data, then node left. So the data should be less than, then that is a left address. If it is greater than, then that is a right node. Okay, like that we are creating the binary tree creation, insertion and deletion. Okay, if the data is less than the node get data, nothing but if any data is existed, the data will be compiled with the particular inserted data. So I have the root node. Suppose I have the root node. So if new data is creating, we have to check that if the entered data is less than the before root data, then that is the the new data will be called as a left node. If it is more than the right, then it is the right side. More than the root node value, that is the right side. So after that we have to return the node. This is the insertion and deletion process. So pre-order traversal. Basically we need, just before that we have created inserted a binary tree. Just we have created inserted. So we have to check that all the elements are correctly entered, all the nodes are linked with the proper binary tree fashion. So we have to check that by using the pre-order. What is a pre-order? I have called the pre-order function, pre-order of root. So when we are calling the pre-order, immediately pre-order function will be linked. So private void type of pre-order. So what we have to pre-order? We have to pre-order the particular nodes. Okay, where is that? That is the binary search tree of kind of data nodes. So if R, here what is that R? R nothing but root node. Where is R? So this is called the R. This R is calling here. That R we are checking. If where is that R is coming? So here the pre-order of root. That is the object argument. So that root we are discussing here. That root here. So that root we are checking. So if our root is null, immediately we can check the, if not null, if it is null, we can, nothing tree is existed. Okay, if it is not null, immediately what is the traversing technique here? Pre-order nothing but first root, next left shell, right shell, isn't it? So if left shell had one more subtree, we had traversed the pre-order fashion, and if right shell has the subtree itself, we have to traverse in the pre-ordered fashion for the right subtree, like that. So system dot out dot print of get data of the root. So for root element, next go to the pre-order. Again it is calling the some recursive function fashion. So immediately we will move to the pre-order. Again it is calling the same pre-order function. So same process will be done. First the subtree root, again child value. So pre-order, you know the recursive function designing. Recursive nothing but function calling itself. Here pre-order is a function, it is calling itself. Okay. So how many times it will be done? Up to the last siblings will be doesn't have any children. So a tree having the number of subtrees, every subtree will be traversal in the fashion of pre-order, and if children's nothing having any subtrees, nothing but any children's its own, so processing will be cancelled. Again it will move to the next step. Okay, it's a pre-order technique, nothing but first visiting the root node, next we are calling the subtree with the pre-order. Again we are calling the recursive function fashion, pre-order function, some get data and left data. Like that we are traversing all the techniques. So in this we have done two classes. One is a binary search tree classes and one more is a insertion. First we are creating a node and get data, set data and get left, right, left we are doing in the first class, and next class we have inserted. Okay, inserted and traversing techniques we have applied in the binary tree is a pre-order fashion. And next, so we are creating a simple class using the pre-order recursive function, recursive BST, whatever the name you can use, it is user defined. So use the main function, create an object. By using the scanner class, we can scan the value. We can give the input to the system, to your program, and creating the BST. Nothing but for the class we are creating the BST is a object of the binary search tree, and we are inserting the elements. 10 elements have created, so all these elements will be entered. Okay, next that we are processing the BST for the pre-order traversing technique for your basic binary search tree. After that we have to close the function. Scan dot close, nothing but it will be closed. So check a value, 10 values we have given, some 12, 10, nothing but it will be represented by using the binary tree, represented by using the binary tree representation with the linked list function. So you can check up that. So 12 is the root, next is the 10, next like that how the data will be inserted. So if the element entered data will be greater than the root, it is the right side. If it is less than the root, it is the left side. Like that the tree will be created, all the elements will be, it is not in ascending and descending order fashion. With the pre-order, first we have to create the tree, binary tree, again we have to traversing with the particular elements with them. Okay, so work out with the example, again check the creation of the binary tree and do the pre-order technique. Okay, this is the basic representation of a binary tree representation. Is a program looking very large, even though it is very simple to understand. First class we are creating a data class, creating a node, getting data, setting data, get the left, get right, set left, set right, and next class we are inserting a node, traversing techniques, and next third class, in that we are creating this main function. So this is a binary tree representation with the pre-order traversing technique.